Hello, I'm Christopher Jans. I'm from Huawei Technologies Canada. I'd like to present this work on behalf of myself and my colleagues, Digital Twin for the Optical Network, Key Technologies, and Enabled Automation Applications. Now, the digital twin we're talking about in this talk is specifically one that is quality of transport or QoT oriented, that looks to assess and predict the transmission performance, really available margin on actual optical connections or prospective ones in some hypothetical network configuration. Planning control operations really require that kind of capability. Optical networks are now reconfigurable. They feature ROADMs, reconfigurable add-drop multiplexers, and tunable coherent transponders where we can select, for example, modulation format, baud rate, coding in order to trade off distance and transmission capacity. With the network reconfigurable, that's very useful. We can be more efficient under evolving traffic loads. Really, we can support ongoing evolution through planning. But of course, transmission performance becomes variable as compared to a fixed point-to-point system. So if we look at various categories of operations, including, let's start with provisioning, that's channel add drop, reroute, restoration reactions to failure, etc. We need this QoT measurement and prediction capability, right? We want to maintain new but also modified, existing modified and unmodified connections within performance bounds without requiring the allocation of excess margin. When we change anything on the network, the coupling of channels through optical amplifiers leads to complex reactions, right? So it's very difficult to maintain a handle on. Additionally, if we're after generalized margin compression, right, we want to squeeze efficiency throughout the network, then we need very good QoT measurement and prediction capability. And those capabilities really are reflected properly in what the industry calls a digital twin, right? We want the accuracy supported by, among other things, up-to-date information, telemetry, type and instance equipment information, etc. Right? Still, these capabilities are difficult to achieve. But one way to look at them is start to inventory them, knowing that we're after both improved operations outcomes and automation of operations. We can start to look at the components of the automation closely. Right, so if we do that, and the canonical such loop is data analysis, decision, action. Right. So first of all, on the data side, the optical network traditionally is pretty poorly instrumented. Right. I mean, really, our stats collection is bit errors, and the key optical performance factors. Right. That yes, ultimately they determine bit errors, but the things we want to look at over a broad range that give us our modeling supporting information directly, such as linear and nonlinear noise. Those things tend not to be measured. When it comes to modeling, really, there's no nothing resembling a digital twin that's out there in use, right? So modeling tends to be for the planning domain, fast executing, accurate device and telemetry supported modeling for real-time performance measurement and prediction just isn't out there. And when we talk about decision processes, this leads to obviously compromises. Configuration, provisioning are performed pretty much blind. Optimization of the network service configuration is generally avoided. And planning tends to be manually driven and I would say performance semi-blind. The optical network, as a result, is largely manually driven. Provisioning, restoration operations are risky in a sense. So we tend to leave the optical network alone. We leave it quasi-static, which kind of runs against the trend of service dynamics and the goal of network reconfigurability. And it means that really we provision a lot of excess margin, right? And that means lost network. Now, advances in optical network instrumentation, this has been a strong focus of industry work for a number of years now. Among the key things we're targeting is direct measurement of linear and nonlinear noise. It's receiver DSPs and coherent systems that really, provides us the signal processing platform opportunity to get at that. So some work that we've seen in the industry, in some cases with connections to my own team. Here's some work that's using fast bit error rate measurements and machine learning on those patterns to distinguish linear and nonlinear noise and measure the two. But an even more straightforward approach that's now part of the family of measurement techniques that are based on signal modulation with pilot tones, right? In this case, we apply a small pilot tone to the coherent signal. We also insert gaps. So basically, the gaps give us ASC noise only, not a nonlinear noise component due to the signal, so we can separate the two. And the measurement of the differential measurement of the effects on the pilot tone versus the rest gives us the ability to very accurately measure the noise levels themselves. And that's part and parcel of a larger set of measurements that we can tackle using pilot tones. For example, if we sweep a pilot tone across an individual channel spectrum, we can get a very good measurement looking at from the receiver end at the net or total channel filtering due to cascaded ROTAMs for that particular channel. And of course, once we can measure that, now going into the modeling domain, we can use, for example, machine learning to correlate measured filter shapes to bit error rate or margin penalties on the individual channels, given their modulation format, baud rate, etc. Okay. So this gets us into, when it comes to modeling, the most important, certainly, device in the transmission system that we need to model is the EDFA, the erbium doped fiber amplifier, because this is what introduces our noise, our linear noise, but also couples channels. Really, the variation in power on one channel will, through gain coupling in the amplifiers, lead to power and therefore also noise variations on other channels. So this is really the thing we need to get right. But the behaviors are notoriously difficult to model well in detail. And really, for the kind of accuracy we're after in a digital twin, we can't just rely on sort of generic physical modeling as we tended to do historically in planning. We need at least type-specific models that are good, and ultimately instance-specific models to account for those detailed variations in behavior one to the other. An approach that we found works, first of all, we tried not to measure or model the gain directly, but the difference in channel gains between the full fill case where all the channels are lit, and that's something we can measure on each amplifier for specific bias level, etc., at the point of manufacture, right? And then we want to model the difference between that and the various so-called partial fill cases where there's some subset of lit channels transiting the amplifier. And if we go through a little math, we realize that the output of that model is something we can use directly to get an answer to between this channel state transiting the amplifier and this channel state, that is set of channels and their power levels transiting the amplifier. What is going to be the change in the gain on every amplifier? And that's really what we're looking for. And it turns out that that's something we can develop models for very well using supervised machine learning. We get a model that itself is amplifier instance independent, but is made in use amplifier instance dependent through the application of that full fill channel spectrum. And it doesn't introduce any real point of complications. Right. So again, seeing how the behaviors are pretty complex in the detail with spectral hole burning, things like that. Here's just some illustrations of measured and modeled gain results across channels under different circumstances of what channels are lit, which are not, power levels of the different lit channels, etc. And obviously, there's a gigantic channel combinatorial state space with 80 or 120 channels, or even more if we get into C plus L band systems. All of them can have varying power levels. So, obviously one has to rely on a lot of data gathered at the model generating stage, and also some judicious choices about how to cover the state space. And the same approach, of course, has proved to work pretty well on the noise figure for those amplifiers, right? And so it turns out that, applying both models to a cascade of amplifiers, we can get very good simulation of the noise and power level evolution. So overall, all this capability we want to put together for a total transmission performance model inside a digital twin. And we found that really the way to tackle this is with a decomposition-based approach, right? Don't try to black box learn the behavior of a system, right? I mean, real systems don't change state often enough to give you a usable model anytime soon. Plus, you're throwing away everything you know about how the system behaves. So really, this kind of decomposition-based approach where we isolate the different factors that contribute to margin or margin penalty, and then we're able to use measurements and modeling together according to what instrumentation or data we may have and what we don't, in all cases of measurement and prediction to get to the answers we want. Right, and that kind of capability we want to package as a digital twin, generally as an analytics utility that fits alongside other such utilities in or adjacent to some converged management control platform, right, where most vendors are going. This is really the object that people call a transport SDN. Right, now in terms of other details of operation of the digital twin, really to support the concurrent operation of a number of applications and the different kinds of scenarios that the different applications may be exploring, we need an architecture that basically allows us to create, operate, and manage dynamically a parallel set of simulation instances, right? And each of these instances has its own QOT model instance created, right, from the template. It has a certain degree of instance-specific data to the degree that the services model, the equipment topology, etc., may be specific to that application and different from the current reflection of the actual network, right? Otherwise, the information is coming directly from the telemetry, topology, service map, etc., that reflects the actual network at that point in time. Right? And further, the information that we're supplying to each simulation case is, in a sense, the best available information in terms of model inputs for those circumstances and at that time. Right? So there's kind of a hierarchy that we may that we resort to. For example, in a greenfield planning case, we may have only nominal fiber link lengths and per length loss figures. On the other hand, once that's operational, we've got the opportunity to measure, for example, channel powers in and out on each OTS link. Now we can measure those fiber link losses. That's now better information. Similarly, in some planning scenarios, we may just use the type average EDFA data for model exercise. On the other hand, on the deployed instances, we have the instance-specific data that we can use to optimize the EDFA model for those cases. We may have modeled OSNR or nonlinear noise available. I mean, there's always a way to model that with the chain that we have. On the other hand, it may be directly measured. In that case, it's a better answer, and that's what we use, right? So now looking quickly at use cases, margin surveillance on active channels, right? That's obviously something we can do. We're measuring for example, the In this case, it's reflected as an SNR margin, but we know where the sort of threshold for meaningful signal degradation is. We can measure continuously and then plot over time the evolution of that, get figures about how far we are remaining in general from the margin edge, so sort of identify what margin we have, average through time, and what the, to the degree that there's an excess margin allocation. And we can track trends for incipient failure signatures. In provisioning automation, we can compute directly the adjustments we need to optical powers to not only to optimize channel margins, we can then examine possible transponder tunings to increase the transmitted capacity, use up some of that excess margin that was spoken about at OFC by some colleagues from Siena. But in general, we can use the DT to compute those optimized launch powers on new channels, how to adjust powers in the existing channels. We can go to channel operation batching and sequencing, try to avoid those transient or permanent impairments to channels, right? And here's some experimental results using our optical digital twin, right? This is a lab-based set of very large 120 channel C-band systems, all with either 5 or 6 OTSs, that is ROADMs, and 5 or 6 EDFAs on each OTS, so 30 ROADM cascades, right? And these are statistical results among many configurations of existing and added channel group sizes and distributions. But what we're comparing is, we just add all the channels, boom, at nominal levels, and we don't change any of the existing power levels, or we add all the channels in one shot, but we've computed optimal levels for those new channels plus adjustments to the existing channels on each OTS, right? And we can see from the data that the number of channels that come up or remain within acceptable power evolutions and optical noise evolutions jumps from 20% to a half up to very close to 100%. That really shows the effect. In general, through the that coupling of optical performance, optical channels through amplifiers, we get this notion of any operation we do introduces some risk to a larger set of channels that are out there. Really, any channels that at some point transit the same amplifiers on some link, right? So risk mapping, the ability to use the optical DT to examine any sort of prospective scenario where we're changing the network state, whether that's an add drop reroute, a failure and restoration, whatever it is, we can identify the performance risk to all of the channels that might be operating and potentially impacted. That allows us to corrective action, right? So as you can see, for example, here, there's a prospective channel add. The channels potentially affected and how are flagged to the user for a choice whether or not to proceed or to carry on with some kind of optimized operation. Once we've done that, of course, we can proceed to dynamic restoration optimization, right? I mean, the identification of risks could trigger the determination of a new restoration map, and that could be pressed directly into active standby state. And of course, any prospective reconfiguration or restoration map can be checked for performance integrity using the DT. Very similarly for maintenance planning, for network planning, whether that's greenfield or brownfield, right? The only difference really being how much of the data is real from the network and how much is really we're relying on that sort of planning level detail. We can tackle generalized network optimization, right? And of course, a lot of these things are applications that require over and above the DT some level of optimization capability, and that gets us into the world of can we squeeze margins, right? Whether can we get away from that traditional end-of-life margin planning uh, uh, mode of operation to whether it's some multi-period general re-squeezing of margin through re-optimization of the network, or continuous sort of when we hit the margin edge, we're making a change, right? But really, we can squeeze a lot of excess capacity out of the network by resorting to things like this. And what helps us is, the tunable coherent transponders, where we're not just choosing the route and channel spectrum allocation for a particular optical path, but we can vary the detailed spectral assignment, the modulation format, baud rate coding, etc. And it does, in fact, this is the hypothesis that increased malleability doesn't give us more resource efficient configuration solutions in principle. And that's something we looked at on a real network. Won't go through details, but it's a large ROADM network in China with sort of a representative reach capacity table for the different possible transponder states, sort of a proxy for the answers that were provided by digital twin. And of course, what we see is, yes, very much as we exploit the tunability of transponders, that increased malleability of the network gives us a much, much greater effective capacity in the network. In some cases, we model as much as a 90% increase in usable capacity on the network. Of course, one wants heuristics to be able to compute the solutions, right? With these added degrees of freedom, ILP solutions become, in many cases, effectively intractable. Heuristics would allow us to get results that approximate optimal solutions, but with much faster execution, so we can consider using them even in real-time applications, right? So I'm not going to spend any time or detail on that. Some very good work has gone on in the industry. Here's one citation from a group around Ruth Bataba at Waterloo that we worked with that had very good work in this orientation. And really just to show this is the idea, right, that we can get very close to optimal solutions as determined by a comparative ILP study. In most cases, right, 95% of cases, we're within, say 5% of optimality. But we can do that with 3 orders of magnitude greater execution speed for the same compute power. Right, so really the QoT-oriented optical digital twin and these kind of optimization capabilities in combination let us tackle and support automation on really a large fraction of the automation use cases that we're interested in on the optical network, and also get at margin squeezing and a generalized improvement in efficiency. Thank you very much.